In September 1940, a small group of British scientists and military officers boarded an ocean liner bound for North America, carrying with them a black metal deed box that they never let out of their sight. Inside this unassuming container, nestled in velvet, was a device no larger than a tea saucer, a block of machined copper and wires that looked more like a peculiar paperweight than a weapon of war. This was the Tizard mission, a desperate gamble by a besieged Britain to share its most guarded technological secrets with the neutral United States in exchange for industrial support. The object in the box was the number 12 cavity magnetron, an invention that an American historian would later describe as the most valuable cargo ever brought to our shores. While the world focused on the Battle of Britain raging in the skies above London, this small device was traveling across the Atlantic to fundamentally alter the physics of the war. It held the secret to generating high-power microwave pulses, a capability that would shrink the massive tower-bound radar stations of the 1930s into compact units that could fit inside the nose of an aircraft. To understand the magnitude of the cavity magnetron, one must first understand the limitations of early radar technology available at the outbreak of the war. The British chain-home system, which had successfully spotted Luftwaffe formations during the summer of 1940, relied on massive steel towers broadcasting long wavelength radio waves. While effective for early warning, these systems were blunt instruments. They could tell you a formation was coming, but they lacked the precision to pinpoint individual aircraft or detect a periscope slicing through the water. Furthermore, the equipment was room-sized, requiring vast amounts of power and stationary infrastructure. The holy grail for radar scientists was centimetric radar short wavelengths that could provide high-definition imaging of small targets. However, generating these microwaves at sufficient power was thought to be impossible. Existing vacuum tubes would simply melt or fail to produce a signal strong enough to bounce back from a distant enemy. The Allies were fighting with one eye closed, able to see the storm coming, but unable to see the individual raindrops. The breakthrough occurred not in a high-tech military facility, but in a cluttered laboratory at the University of Birmingham in early 1940. Two physicists, John Randall and Harry Boot, were experimenting with the concept of a resonant cavity, effectively applying the principle of a whistle to electromagnetic waves. They drilled a series of circular chambers into a solid block of copper and placed a cathode in the center. When high-voltage electricity was applied and the block was placed in a magnetic field, electrons swirled around the center, blowing past the openings of the cavities and causing them to resonate, much like air blowing over the top of a glass bottle. The result was a device that didn't just produce microwaves, it screamed them. When they first tested the device, the power output was so unexpectedly high that it nearly burned out their measuring equipment. They had hoped for a few watts of power. The cavity magnetron produced nearly 500 watts, and soon, with refinements, would produce pulse power in the kilowatts. It was a quantum leap in technology, akin to trading a candle for a searchlight. The implications of Randall and Boot's invention were immediately apparent to the British scientific establishment, but the industrial capacity to mass-produce the complex copper blocks was lacking in a country under constant aerial bombardment. This led to the pivotal moment at the Wardman Park Hotel in Washington, D.C., shortly after the Tizard mission arrived. The British delegates revealed the magnetron to their skeptical American counterparts. When the Americans tested the device at the Bell Telephone Laboratories, they were stunned into silence. The seemingly simple block of copper produced 10 times more power than the most advanced American transmitters of the time. This moment of technology transfer ignited a frantic industrial effort. The United States, with its vast manufacturing base, established the Radiation Laboratory, or RAD Lab, at MIT. It became a factory of physics, employing nearly 4,000 people, dedicated solely to exploiting the potential of the magnetron. The RAD Lab would eventually design over 100 different radar systems, turning the British prototype into a mass-produced standard of Allied warfare. The first and most critical application of this new centimetric radar was in the darkening skies over Germany. British Bomber Command had been suffering horrendous losses during night raids, often missing their targets by miles due to poor visibility and navigation. The Magnetron allowed for the creation of the H-2S radar, a device small enough to be mounted in the belly of a Lancaster or Halifax bomber. Unlike previous systems that looked for radio echoes from other aircraft, H-2S looked at the ground. The short microwaves generated by the Magnetron mapped the terrain below with photographic clarity, distinguishing between the flat reflection of water, the scattered reflection of open fields, and the hard, bright return of built-up cities. For the first time, Allied pathfinders could see through cloud cover and darkness, identifying the specific bends of rivers or railroad yards. The cavity magnetron turned the cover of night, which had previously protected German industry, into a transparent veil. However, the most desperate need for this technology was in the freezing, turbulent waters of the North Atlantic. By 1941, German U-boats were slaughtering Allied merchant shipping with impunity, creating an air gap in the mid-ocean where convoys were defenseless against wolfpack tactics. The U-boats attacked at night, surfacing to use their diesel engines and high speed to run down the slow-moving freighters. Early airborne radar was ineffective because its long wavelengths reflected off the waves, creating sea clutter that hid the low profile of a submarine. The cavity magnetron changed the equation entirely. The new ASV, air-to-surface vessel, Mark III radar, powered by the magnetron, used a wavelength so short that it could detect the conning tower of a U-boat or even just its snorkel from miles away, regardless of the weather or the time of day. The hunter suddenly became the hunted. The introduction of centimetric radar into the Battle of the Atlantic in 1943 catalyzed a sudden and catastrophic shift for the U-boat crews. German submarines were equipped with METOX receivers, devices designed to listen for the pulses of Allied radar so they could dive before an aircraft attacked. But METOX was designed for the old, long-wavelength radar. The high-frequency pulses of the cavity magnetron were completely invisible to German sensors. U-boat captains would be cruising on the surface at night, feeling safe in the silence of their receivers, only to be suddenly illuminated by the blinding lee light of a diving B-24 Liberator. The surprise was total. In May 1943 alone, known as Black May, the U-boat arm lost 41 submarines, a quarter of their operational strength. The magnetron had rendered the U-boat's primary tactic surface attacks at night suicidal. It was the technological checkmate that won the Battle of the Atlantic. Simultaneously, the cavity magnetron was revolutionizing the air war over Britain. The Luftwaffe had switched to night bombing to avoid the Spitfires and Hurricanes that ruled the day, launching the Blitz on London and other industrial centres. British night fighters, like the Bristol Beaufighter and later the de Havilland Mosquito, were initially flying blind, reliant on ground controllers to guide them. The miniaturization afforded by the magnetron allowed for the installation of AI, airborne interception, radar, directly into the nose of the fighters. The radar operator, sitting hunched in the back of the plane, could stare into a cathode ray tube and see the blip of a German bomber miles away in the pitch black. The centimetric radar was so precise it could guide the pilot into firing range before he ever saw the enemy visually. The invisible German bombers were suddenly being swatted from the sky by opponents who could see in the dark. The technological dominance of the magnetron extended to the Pacific theater as well, where the U.S. Navy utilized the SG radar to devastate the Imperial Japanese Navy. In the nocturnal naval battles around Guadalcanal and the Solomon Islands, Japanese optical superiority, their sailors were trained intensely for night vision, was initially a decisive advantage. But as American ships began to deploy magnetron-based fire control radar, the balance tipped. US battleships could fire 16-inch shells at targets over the horizon, in total darkness, with terrifying accuracy. The radar-directed gunfire at the Battle of Surigao Strait was so effective that Japanese survivors described the shelling as godlike in its precision. The Magnetron allowed the US fleet to fight a 24-hour war, tracking enemy movements and directing fire solutions while the Japanese crews were still squinting into the gloom. The Germans were eventually alerted to the existence of this new technology, but the realization came too late to save them. In early 1943, a British bomber carrying an H-2S radar unit was shot down near Rotterdam. German technicians recovered the smashed remains of the device, which they dubbed the Rotterdam device. When they analyzed the copper block of the magnetron, they were horrified. Their own scientists had dismissed centimetric radar as a pipe dream, years away from practical application. Yet here it was, mass-produced and operational in enemy hands. The discovery sent a shockwave through the Luftwaffe command, as they realized their entire air defense network was obsolete against this frequency. They frantically attempted to develop countermeasures and copy the technology, but the industrial and scientific gap the Allies had opened up was unbridgeable in the crumbling economy of the Third Reich. The mass production of the cavity magnetron was a triumph of manufacturing engineering as much as theoretical physics. Companies like Raytheon in the United States took the delicate, hand-machined laboratory prototypes and figured out how to stamp them out on assembly lines. The intricate copper chambers, which originally had to be drilled with high-precision tools, were adapted to be produced using laminations stacking sheets of stamped copper like a deck of cards, which sped up production exponentially. By the end of the war, the price of a magnetron had dropped from thousands of dollars to just a few tens of dollars. This democratization of advanced technology meant that radar was not just for the flagship. It was for the patrol boat, the escort fighter, and the mobile artillery unit. The Allies flooded the battlefield with microwaves, creating a sensory dominance that the Axis powers could never match. The sheer versatility of the magnetron led to its integration into the proximity fuse, or VT fuse, another game-changing innovation. While the VT fuse used different vacuum tube technology for its specific radio frequency, the push for miniaturization and high-frequency ruggedness driven by the magnetron research at the Rad Lab created the ecosystem where such inventions could thrive. The culture of the boffins, the slang term for the scientists merging with the military brass, created a unique synergy. Physics was no longer abstract. It was tactical. The feedback loop was immediate. A pilot would report a problem with sea clutter in the morning, and the scientists at the Rad Lab would be soldering a fix or designing a new antenna by the afternoon. This agility, powered by the versatile heart of the magnetron, kept the Allies one step ahead of every Axis countermeasure. As the Allied armies pushed across Europe, mobile radar units powered by magnetrons tracked enemy movements and directed tactical air support. The SCR-584 radar, a gun-laying system, was particularly devastating against the V-1 flying bombs that Hitler launched against London in 1944. The magnetron-powered radar could track the fast-moving, pilotless buzz bombs with such accuracy that anti-aircraft guns, aided by proximity fuses, were shooting down nearly 80 of them before they reached the city. The technology had come full circle. The device that was sent away from Britain in a black box in 1940 had returned, multiplied 1,000-fold, to shield the island from the final vengeance weapons of the Nazi regime. It was a technological shield forged in the fires of the Blitz. By 1945, the cavity magnetron had saturated every theater of the war. From the nose cones of B-29s bombing Japan to the convoy escorts in the Atlantic, the hum of the magnetron was the background noise of victory. But as the war ended, the question arose, what to do with this massive capacity for generating microwave energy? The factories were churning out these copper hearts, But the demand for tracking U-boats had evaporated. In 1945, Percy Spencer, a self-taught engineer at Raytheon, who was a genius of the Magnetron production line, was touring one of the testing labs. He paused in front of an active Magnetron radar set and noticed a strange sensation in his pocket. A peanut cluster bar he had been saving for a snack had melted into a sticky mess. Intrigued, Spencer did not dismiss the event as a nuisance. He possessed the curious mind of an inventor. He sent a boy to fetch a bag of popcorn kernels. He placed the kernels in front of the magnetron horn, and within moments they popped and scattered across the lab floor. He then tried a raw egg, which exploded in the face of a skeptical colleague. Spencer realized that the microwave energy, which had been used to bounce signals off steel hulls, was agitating the water molecules inside the food, generating intense internal heat. The death ray of the U-boats was actually a highly efficient heat source. This accidental discovery marked the transition of the magnetron from a weapon of destruction to a tool of domestic convenience. Raytheon filed a patent for the high-frequency dielectric heating apparatus in 1945 and soon built the first prototype, the radar-range. It was a behemoth, standing nearly 6 feet tall, weighing 750 pounds and costing $5,000. It was water-cooled and required a plumber to install. It was a far cry from the kitchen counter appliance of today, but the core technology was identical. The very same cavity magnetron design that had hunted submarines in the North Atlantic was now being marketed to restaurants to cook hot dogs in seconds. It took decades for the technology to be miniaturized and cheapened enough for home use, but the lineage is direct and unbroken. Every time a microwave beeps in a modern kitchen, it is echoing the pulse of a WWII radar set. The legacy of the cavity magnetron is one of the supreme ironies of the 20th century. It is a device of extreme violence that became a symbol of suburban domesticity. The Rad Lab at MIT, which disbanded after the war, seeded the American electronics industry, leading directly to the rise of Route 128 and eventually Silicon Valley. The scientists who built the magnetron went back to their universities, their work declassified years later, often receiving little public recognition compared to the physicists of the Manhattan Project. Yet, their impact was arguably more immediate and widespread. The atomic bomb ended the war, but the magnetron won it, day by day, battle by battle, by granting the Allies the superpower of sight. Today, the number 12 cavity magnetron, the original prototype brought over in the Tizard mission, sits in a museum, a silent block of copper with drilled holes. It is smaller than a brick, yet it carries the weight of history. It represents a moment when the fate of the free world hinged not on the size of a battleship or the caliber of a gun, but on the resonant frequency of a copper chamber. It is a reminder that the most decisive weapons are often the ones that make no noise, the ones that sit quietly in a black box, waiting to unleash a new spectrum of possibility upon the world. The story of the magnetron also challenges our perception of war technology. We often think of tanks, jets, and missiles, but the electromagnetic spectrum was the true battlefield of WWII. The ability to control and exploit microwaves gave the Allies command over the invisible architecture of the air and sea. The Germans and Japanese, despite their engineering prowess, were fighting in the dark, blinded by their inability to generate these high-power centimeters waves. The magnetron was the lamp that lit the room, exposing the enemy S movements while keeping the Allies in the shadows. Ultimately, the cavity magnetron serves as the bridge between the industrial age and the electronic age. It proved that electronics were not just for communication, but for sensing, heating, and controlling the environment. From the weather radar that tracks a hurricane to the speed gun of a traffic cop, and yes, to the reheating of yesterday's coffee, the children of the magnetron are everywhere. It is the unsung hero of the Allied victory, a palm-sized piece of metal that saved Britain, doomed the U-boat, and then quietly retired to the kitchen, hiding its warlike past behind a digital clock and a glass turntable.